Institute, Space Research Institute of the Russian Academy of Sciences, and I asked him, or he suggested also to give a broad, short introduction about himself and the work in his group. And I should apologize. I will probably receive a phone call during his talk because, as you may know, my computing account was closed down and is still not reopened again. So I'm rather nervous about that. So, Rako, please.
Thank you. First of all, I am very grateful to Axel for inviting me to Nordita. And I am petrosyan. As can you see, I am head of this theoretical section at the Space Research Institute of the Russian Academy of Science. And okay, everybody knows that what is Academy of Science, and everybody knows what is theoretical section. This is something stupid because in all Russian Academy of Science Institute, you should have theoretical section or theoretical department, because there was tradition from Landau, from Ginsburg, and so on and so on. And head of department or section should be best scientist, but this is not the case for me. I think so. And first head of our section was academician Sagdeev. Then he retired from his director post. He got this position, and you know what is a tradition? Tradition, when somebody from theoretical science is retiring, they close this department or section and do new. Second was maybe you know Galiev, and now unfortunately I am doing this work. Unfortunately, because this is young department, and in Russia, if you have young department or young division during 5 years, you are not reducing. No any government person can reduce your division. So everybody wants to come to theoretical division, and I always need to tell them no, because I don't want to be big manager. So, head of theoretical section. What is our interest? Our institute is working on 3 directions. First direction is, of course, astrophysics. It's high energy astrophysics. Everybody knows Sunyaev's name. Zildovich initiated this direction. And these people are doing mostly data processing of high energy experiments. And early days, when Sunyaev was young, he did this very excellent work with Sunyaev Shakur about disks, everybody knows. Other topic in our institute is planetary science. Main task of our planetary science again is studies of Mars, studies of Venus, and comparative planetology of this. And connections with Earth science, of course, but Earth science is weakest point in our institute, because Earth science in our institute started from military studies, and most people are already gone, and we don't have good tradition to do civilian Earth studies. And of course, space plasma studies and plasma astrophysics. This is led by Sagdeev, then by Galeev, now by our director. So, and my responsibility is to help all these projects in modeling efforts and in interpretation data, in theory development. So I'm not so free person like many theoreticians who may do what they want, because I always need proof that institution need me. And this is mainly directions in which works my team presently. But team, we have part people who are not working with me, but they are on my division. And some people with my students, this is my part. First topic is void turbulence. Void turbulence, tradition in Russia. And you probably know very well, it comes from Moiseyev's work. We were very much interested in long-lived vortices. And it was idea, since vorticity equation and magnetic equations are similar, to try to find something like inverse cascade, analog of dynamo. And there were some works which was done by Moiseyev and many times criticized, sometimes accepted. And what was my inclusion and what was my interest presently? I did turbulent coiled flow. Why I did turbulent coiled flow? There was idea that if you have convection and if you have compressibility and you put helical turbulence and using mean field theory, classical theory like we use book, transmitted in Russia. So you always get something like non-trivial terms, like alpha denominator. But problem is, if you have compressibility, and so you need to put also acoustic waves, it makes story much more complicated. If you have turbulence, convection, you have some non-homogeneous temperature gradient, it's hardly expect homogeneous turbulence in this situation. And what we wanted to construct some flow for which we can simply try to obtain this non-trivial terms related inverse cascade. And what we did, we used coed flow. Coed flow is linear flow, you know. And it produced homogeneous Reynolds stresses at least. So you can consider at basic state homogeneous coed flow. But the only problem is that it's anisotropic. And what we did, we suggested, with using rapid distortion theory, this anisotropic tensor, and then put all this to mean field theory and obtained some equations. We show it inverse energy cascade. It was published in Physica Scripta. And what we are doing now with one of my students, we are interested in getting such effect without initial helicity. We want to have just rotation which produce helicity. Rotation which acts on correlation function and gives you non-trivial Reynolds stresses. And we also derived mean flow equations, and we derived for convection, without convection, and found some new motions in rotational flows which are subjected to turbulence and to rotation, which are similar to helicity gives, and now trying to analyze this. This is one of direction of our work. Second direction is MHD turbulence, but it's interesting because we are space research and all our directors are plasma scientists. And it will be my talk about large eddy simulations, so I will describe later. Aerosols in boundary layer. Why we started this project? Because we had in Russia an interesting project, landers on Mars. And what is very difficult technical and also theoretical, when you land on Mars, you have enough dust. This dust is lifting. And you have lander, boundary layer, planetary boundary, and dust. And you need to be able to predict. Yeah, I'm waiting. And you need, should we wait him?
No.
No.
That'll
Okay.
take a while.
And we need to be able to predict opacity around this, Mars lander. And it should be done not with supercomputing, because when you are managing this project, you need to do this sitting on your office and on small computer. So you need to develop very interesting model, which is very fast, which is very good accuracy, and which gives good predictions. And we did this also, we developed this model. What is difficulty in any boundary layer modeling in planetary science? Difficulty is viscous equations. When you have viscous equations, when you have very small viscosity, all solutions of differential equations are unstable. It's quite difficult to do stable computations, especially if you have complex terrain, because it's very difficult to work with fractured grids, you understand? And what we did, we developed some model based on scheme viscosity. We use non-viscous equation, but viscous finite difference schemes, so that to describe viscosity which you need for boundary layer. In this case, we developed very interesting algorithm. Who wants, I will show results. I will not present here, just idea, but I have on my computer these computations. But it was initiated by our studies for Mars. Show water theory and hyperbolic system. Why we started this project? First of all, shallow water is our atmosphere. Shallow water is our ocean. And what is important, shallow water is magnetic tachycline, but this is magnetic MHD. For these reasons, we need to be able to solve shallow water equations on complex boundaries. When you do complex boundaries, okay, you always interpolate complex boundary with some steps. And then you always use solution in step vicinity, and then you match this with all other solution in all other domain. And what happened, what we observed, that people do this, but what we observed, that Sherlock equations on step don't have unique solution. Solution is not unique, and strongly depends on, okay, accuracy of your computations. That's why, okay, we publish this. We had many problems with science community, because when they understood that this is not unique, how to do unique. So we proved non-uniqueness of this solution, and we developed many, okay, at least two ways to make solutions of shallow water equations unique, which is very important. One way was we developed some new shallow water approximation, which gives you a unique solution on step. It's based on okay, idea is when you develop shallow water theory, who knows, you neglect vertical acceleration. And also you neglect non-homogeneity of horizontal winds or horizontal flow. Idea is to take into consideration in some asymptotic manner this non-homogeneity. When you do this, you simply get depth averaged shallow water approximations, and you simply get new, again, shallow water equations, but extended shallow water equations, which have unique solutions. Another idea was, if you have shallow water equation on step, subdivide shallow water equation by two sublayers, which allows you have unique solution for any layer independently. This is also done, and I have this on my other PowerPoints. This was our main achievement, and what we did, we developed universal code which allows you to solve these shallow water equations in complex area without any problems with this non-uniqueness when you approximate complex area by steps. Now we are extending this for MHD. And recently started three other projects. One is double diffusive convection. Double diffusive convection when you have two species and you have something, some convective instabilities on this double diffusion. And my motivation was because we have space projects to fly to Europa. Europa is a satellite of Jupiter. And we need to understand thermal structure of Europa surface. To understand thermal structure of Europa science, we need, because we also went on this Europa science, we need to develop double diffusive convection in a very difficult situation, when you need to put into consideration compressibility. So two species, two diffusion, convection, and compressibility, which is quite difficult. And what we did with one of my students, we use anelastic approximation. This some approximate possibility to put compressibility. We did full linear stability, and we did low nonlinear instability. We developed a theory about threshold of instability. And now we are doing computations for double diffusive convection. Kinetics of aerosols in presence coagulation evaporation. This is also new topic. What happened? We had problem in Earth science and even on Mars, and even in Triton, to understand properties of clouds and so on and so on. And people are doing computations with using Smolhovsky equation. Smolhovsky equation contains some empirical constants, which is quite difficult. This is not difficult when you do Earth science, because you can make measurements, but it's difficult when you do planetary science, because you don't have even data. So what we did, we are working with Boltzmann equation. So we write Boltzmann equation in presence of turbulence, coagulation, and evaporation. And with one of my also students who is now working in bank, not in science, we found some analytical solutions, exact solutions to Boltzmann equations. And last topic is last new project we started also at the end of last year is kinetic turbulence, kinetic plasma turbulence. There are many objects like solar wind where you can't work with fluid dynamics. You need just to write kinetic equations once in fast space to study turbulence, like Shikochikhin is doing. People use gyrokinetics, but gyrokinetics has very small applicability domain, especially in not only in astrophysics but also in fusion plasma. And idea is to develop real massive code. It's a little bit ambitious, but from theoretical point of view it's not difficult, because massive equation is Hamiltonian system. If this is Hamiltonian system, so very simple, you will find, okay, these canonic quantities, and very simple formulate all these finite volume methods. But the only problem is that you have highly dimensional space, fast space. People use only one fast space, and we use 3 fast space. And what we did, what is the level of this project, we now have very good solver for massive equation in 6 space dimensions, 1 t, 3 space direction and 3 fast direction. What we are now doing, we are coupling this with Maxwell equation, which is not difficult. Difficulty is Maxwell equation works well and massive equation works well, but when you do joint computation, you have problems with scales, and we are working on this, how to improve our code. Okay, now I'm going to...
So, you have a Vlasov solver for either?
Vlasov solver for kinetics. For kinetics. But if you have Vlasov solutions, you have, how to say, distribution function, you may do all
So is yours based on finite volumes?
Finite volumes, yeah.
How much better is with respect to peak, for example, particle?
But it's Eulerian code. This is particle code, Lagrangian code, particle nonsense. And our code is Eulerian. For many reasons, in space observations, Eulerian code is not. Particle is good for fusion. Okay, but our achievement is that we have highly dimensional fast space, 3-dimensional, which is good and all. Now I'm going to our MHD turbulence. Okay, MHD is well known here, and there are 2. Everybody knows what is turbulence. It's very difficult to study, many modes, non-linear, 3-dimensional, and it contains different scales: integral scale, inertial scale, and viscous avalanche. So my tool to model turbulence is, of course, direct numerical simulation. But direct numerical simulation, when you do this modeling, you always are restricted to your hardware. Okay, so, and from engineering community, and we have many successful computations in atmospheric community based on large eddy simulations. And idea is to extend large eddy simulations method for MHD studies. But for present, MHD turbulence, not dynamo still. But there are some people who are trying to extend this for dynamo, like Yannick Ponty. But we are not working now at present situation with dynamo. So our goal was to develop large eddy simulation for compressible MHD, which is difficult. And what is large eddy simulation? Large eddy simulation is just to use full equations. You make filtration of these equations using universality of small scales of turbulence. Then you have some subgrid scale terms which are similar but not the same as Reynolds terms. And then you parameterize these scales. Then you validate this subgrid scale parameterization. You validate comparing the subgrid scale parameterizations with direct numerical simulations, and then you select best parameterizations, and what is important, you try to apply this to some real space tasks. Okay, this is our normal MHD model. This is MHD model with adiabatic gas, which is normally using in space plasma. I will show many difficulties which come out if you use heat conductivity. This is density equation, impulse equation, magnetic field equation. Filtering operation. So your turbulent flow subdivide on small scale and large scale, but large scale is not Reynolds averaging, it's also turbulent. And you use special filtering procedure. In our it was Gaussian function. There are other filters, top hat filter and Fourier cutoff filter. And you obtain filtering equations. You can see that if you make filtering, you obtain many terms due to nonlinearity of compressible equation is third order due to variable density. Yes. So that to avoid these difficulties and use all experience which come from normal non-divergent or non-compressible flow, we use Favre filtering. I think everybody here knows, but this is explanation of Favre filtering. This is weight averaging filtering. Definition is Favre filtering, and you have definition of velocity filtering. Same you use for other quantities. And properties is that filtering of fluctuations is not zero. Okay, and filtering of filtering is also not the same, because this is turbulent. With filtering quantities you may put and study any other statistics. So now you can see filtered MSD equations. What is here with tau u and tau b, we designated these new terms which arise due to nonlinearity. There are always such terms when you, as a average equation, as a filter. So we have terms which are subgrid scales or subfilter scale. The only problem is these terms are well known. From normal fluid dynamics, the only term is that this is rho density, which is not used, and these are magnetic terms. So there were theories of such terms for compressible fluid flow, and there were theories of such terms and parameterizations for non-compressible but magnetic flow. And our main task was to extend and to introduce effect of compressibility and magnetic fields. So we extended all well-known theories for subgrid scale models which come from normal non-compressible MHD to compressible case. This is viscous-Magurinsky model, where turbulent viscosity and filtered and subgrid scale quantities depend on large-scale strenuous tensor and large-scale magnetic rotation tensor. This is viscous. There is Kolmogorov model. It was also developed by Daniel Karachi, which is based on Kolmogorov subgrid energy dissipation. And everything can be obtained by using dimensionless analysis. The only problem is, again, correctly to put density. Cross-helicity model, parameterization based on cross-helicity, which is integral of scalar product of velocity and magnetic field. Scale similarity model. This is non-viscous model. It was most worst model, but we try to use it also. And it's based on the assumption that the component of subgrid scale most active in the energy transfer from larger to small scale can be estimated with sufficient accuracy from the smallest response case. So you use double filtering. And mixed model, which is idea of this scale similarity and Smagorinsky model. We expected that these two classed models will be best for modeling, but the results were very different, which is, still we don't understand why. Okay, this I explained filtering of normal polytropic gas equation. Polytropic gas equation, when you filter, you get only terms which are well known from compressible neutral fluid or magnetic but non-compressible, and just combination of this. You don't have principal terms, you just only need to put variable density. But when you have MHD heat conductive, so you have equation for total energy. And it is, okay, again, performing of averaging gives you new subgrid scale motions. But what is the problem? Problem is that you have in total energy equation magnetic field, and you get principally new subgrid scale terms which don't have analog in normal neutral compressible fluid and non-compressible magnetic fluid. Nothing known. So these are subgrid terms for heat conducting plasma, and these are principally new terms. These are very simple because these are, have analog on a polytropic gas, on adiabatic gas. These are due to appearance of magnetic fields in energy equation. And you need to provide theory for this. And again validate to be sure. These are models for subgrid scale terms. Of course, solutions of heat conductive compressible is much more difficult. It's very difficult to validate all 5 or 6 parameterizations, and we use Smagorinsky model for normal magnetic and velocity stresses, because Smagorinsky stresses show the best results for adiabatic gas. And we developed some parameterizations for these new terms based on generalized central moments. So we computed second moment and we neglected third moment. Yeah.
I mean, that was exactly the thing you wanted to explain, right?
Hmm?
So I thought you wanted to exactly explain the third moments now.
Why I wanted to explain? I compute second moment and I neglect third moment. I just my problem is now if it works well or not works well. When we sent this article to Fish Fluids, both referees said that they don't trust this, but they consider this so important that they recommend it to publish. I never get such review. So, based on just neglecting third moments, we developed these parameterizations for these quantities and put on equations. This is new part. It takes a very huge algebra because it's, you know, vectorial, tensorial, and so on and so on. But at least we did. Then I'm showing results of computations. How we validate our LHD simulations. We just make direct numerical simulation. We make filtered equations without any parameterization, just neglect. And we do computations for all parameterizations that we have. We write this on conservative form equations, finite difference numerical code, fourth order accuracy, third order low storage Wunderkutter method for time integration, current Friedrich-Levy stability conditions, on time step, Gaussian filter of the fourth order accuracy, and skew symmetric form of nonlinear terms. And first what we did, we validated this for decaying turbulence. We use simple DNS because we don't want it, still is not parallel code. That's why we use just DNS for 256 and for alias for 64. This is when people start new alias somewhere. This is main, okay, initial step where they prove the results. And we do periodic conditions. Case studies. We did 7 cases. Reynolds E is Taylor Reynolds number, Reynolds is normal Reynolds number, Reynolds M magnetic Reynolds number. We selected this by this way so that not to have dynamo, because we have decaying turbulence. Magnetic sonic numbers and magnetic Reynolds number, and magnetic sonic Mach numbers and magnetic Mach numbers. So, what kind of computations we made? We made, okay, different computations. Solid line is no model, is direct numerical. Smagorinsky model is dashed. Kolmogorov model is dot. Cross-helicity model is black point. Scale similarity is plus, and dash dot is mixed model. And what we computed, I just show what kind of computations we made, then I will do some analysis. Kinetic energy, cross-helicity, magnetic energy. Then we did molecular dissipation, kinetic energy sub-bit scale dissipation, magnetic energy sub-bit scale dissipation, everything which is possible. And trying to compute some Reynolds stresses from this. And we also analyzed kurtosis, because we were interested in what extent it is possible to characterize non-Gaussianity, you understand, of flows by LAS, or even some people use LAS runs to restore probability density functions. That's why it's interesting to see kurtosis and skewness. If you know kurtosis and skewness, you understand non-Gaussian properties. Okay, let's say kinetic energy, results of kinetic energy for sonic magnetic number 1 and sonic magnetic number 0,2, and for Reynolds magnetic numbers 2 and Reynolds magnetic number 20. You know.
So MS means Alvin speed over.
Yeah. Huge problem for me and for my team is what is our weak point, analyzing of results of computations, because it's not difficult to do theory, it's not difficult to develop codes, but because we are Russians, but then we have difficulty to analyze when we have these runs. What is main outcome from kinetic energy studies? For kinetic energy, large divergence of LES results was observed with decrease in magnetic Reynolds number, using various sub-bit scale clauses. The scale similarity model shows the worst results, however the other sub-bit scale clauses increase calculation accuracy. The changing of Reynolds number produced quantitatively similar results, as the initial conditions of velocity and magnetic fields are the same, and Taylor and Reynolds number does not have a significant impact on choice of subgrid parameterization in our computations. Mach number exerts essential influence on results of modeling. The divergence between DNS and LAS for kinetic energy increase with Mach number. And generally, which is more important, Smagorinsky models and cross-helicity model give best results when comparing with direct numerical simulations for this kinetic energy. Magnetic energy, again, these are results of magnetic energy, and conclusion is the difference between subgrid scale models for magnetic energy decrease with reducing magnetic Reynolds number. And all models for magnetic energy give good agreement. This is different because here we had only two models which give good agreement. The effect of subgrid scale closure increase with magnetic Reynolds number for modeling of MHD turbulence, but the rate of dissipation of magnetic energy decrease with increasing magnetic Reynolds number. Best results shown by Kolmogorov, Smagorinsky, Kolmogorov, and cross-helicity. Here we have three choices.
So when you talk about cross-helicity, you mean actually finite net cross-helicity?
Yeah, it's V and B. Okay, these are computations we want to predict cross-helicity of U turbulence. Again, for this similar parameter, and for cross-helicity, the influence of subgrid scale parameterizations increase with magnetic Reynolds number. Scale, again, scale similarity model demonstrates worst results in presence of adequate SGS parameterization, and Smagorinsky model, again, and best results, and also cross-helicity, of course. So, after this, this is just preliminary conclusion that what we showed is that large edge simulation may be, okay, normal tool for study of turbulence, depending on what you want. Again, still without dynamo.
There is a there is a parameter in this Magorinsky model.
Hmm?
There is this parameter in this Magorinsky
Yeah.
model. Do you have the possibility to actually determine?
Yeah,
the
there
best
here is
set?
special procedure, dynamic
Yeah,
procedure developed Germano. You use one filter, you use second filtering of filtered equations. You have some relations, you have some cost function, and you use. Okay, you need special presentation. There is special strong, and there is written in our article and in Germano. In our article is written for compressible MHD, but in general, fluid dynamics was developed by Germano. These are just preliminary results for heat conductive. This is just to show that our very nested or very strange or simple parameterization of these new terms in heat conductive even gives you good agreement with direct numerical simulation when you use our parameterizations and Smagorinsky for other quantities. So now, after development, we decided to use this for some astrophysical problem, for some space problem. Otherwise, people will tell in my institute that they are doing fluid dynamics, not doing space. It was interesting observation in local interstellar media. In interstellar media, in diffusive interstellar media, that you have density fluctuations which are homograph-like. And they reproduce density fluctuation of fluid flow, non-compressible fluid flow. And idea is just to try to use advantage of these larger simulations to reproduce this regime and try to explain. Because what is the idea? If fluctuations are same spectrum like fluid, normal non-compressible fluid, this means that density is passive scalar. This means that initial high Mach number flow became low Mach number, and we have near incompressible region. The density is passive scalar. And idea is to define this near incompressible regime. So our computations were made using larger simulations with Smagorinsky model, with our adiabatic, Reynolds number 2000, sonic Mach numbers, and Alfvény and Reynolds magnetic number 200, ambipolar diffusion, and again we do periodic computations. And what we found in our computations, we found that turbulent small-scale Mach number with time is reducing. So it's transition from supersonic to subsonic regime observed. And these are results of divergence, velocity divergence. It's also we show that initial higher divergence became weakly compressible. Then we will go to spectra. These are properties of plasma magnetization. So this means that during this regime, plasma became losing its magnetic properties. And what is most important, spectra, because these are turbulent kinetic energy spectra, and this is a normalized kinetic energy spectra, which are homograph-like.
Why is that? Oh, -3. -3. That's which case is that?
Yeah, it's normalized, it's K minus 5/3.
Yeah, but it says -3 on the left-hand plot.
Yeah, it's something, some misprint should be.
But you mean it should be 5/3, or what do you mean?
Yeah, it's 5/3 here, after normalized. The kinetic is
But I mean, you do see the bottleneck effect.
Huh?
You do see a bottleneck effect.
Here I see bottleneck effect, yes, but this is because my computations are not so accurate. And okay, it's it's at least again bottleneck effect which we are discussing. But I don't know.
But you don't see the same thing on the left-hand plot.
No,
So these are
no,
different
it's
things.
after normalization.
Yeah, what do you-
I even don't remember how we did this picture. No, here we did normalization, so they find this from decaying turbulence to define inertial interval. I need to check with an article how we did this, how I...
What's the decay rate of your turbulence?
Huh?
How long does it take to get from supersonic to subsonic?
Oh. You mean in time?
Yes.
You had some power, some decay, the double logarithmic decay laws beforehand. A few pages ago, you had the decay laws. Maybe we see it from there. Where you compared the different.
Yeah, but that time, how much would be?
That's linear scale. I thought we wanted logarithmic, twice double logarithmic scale. You had such plots, I thought. Right? That's what you wanted.
Yeah.
Well,
I mean, if I can start with the supersonic turbulence produced by supernovae, how much it
No,
would take
no,
to
no, no.
this
It do not mean that this is universal regime. This means that you can find this regime. This do not mean that any supersonic turbulence.
No, I know, but how long it will take to get to supersonic?
It's 1.5, but in okay.
I mean, what time is that? It's added turnover time?
Yeah, it's a bit another time. We need to again check an article because it was 2 years ago.
but the decay is normally a power law. A power law is the t to the minus 1 to 1.2. And I don't think that actually changes in the supersonic regime.
No, I mean, we just want to have an idea of the typical times for the ISM to dissipate.
These are density spectra. This regime about when supersonic turbulence became sonic and then the density is something like passive scalar was developed in asymptotic methods by some people. So there were some asymptotic solutions, and our idea is just to find this from three-dimensional computations, if it's possible to find this regime. And the idea is to see if there is a regime where you have density which reproduced in principle of spectra of velocity. And this is the dependence of spectrum with time, how it changes interval, and what is more important for these people who are observing interstellar media, which you can't observe from asymptotic solutions. If you have some runs, you may study anisotropic properties of this diffuse interstellar media, study this Chabalin angle. So, my outcome is that, okay, we found at least one task in space science where it's, okay, important and interesting, where you can get results which are interesting from experimental point of view. And what we are doing now, okay, we are doing fuzzy turbulence with using Lundgren parameterization, which I give you, and we developed these parameterizations, and we found this self-similar, at least possibility to find self-similar regime with larger dissimulations. But I don't know if we obtain this bottleneck. I need to come to Moscow and to see, which is important. Thank you very much.
Thank you very much. Any questions, please?
But there are also other, now there are people like Paduan and people on this university who are doing computations with Godunov methods, high Mach number formulas. And what people say in this situation, if you do accurate computations with high Mach formulas, you have direct numerical simulations. But if you have nested computations, you have larger dissimulations. This is something like implicit larger dissimulation. And this means explicit. So
Yes.
it's something which is going direction to astrophysics. There are some teams which are doing code comparison and so on and so on.
So you introduced this, or you used this Fourier filtering.
Yeah.
Which in some sense subsumes the density dependence, and the density seems to disappear from and there's no trouble with density, it looks like. So what is actually happening?
Because for filtered quantities,
Yes.
for Faber quantities, equations are similar like normal for dynamics. You don't have extra terms due to, equation became second order,
But
nonlinear.
does anything change physically?
Nothing. When you do after this filtering, you recompute. It's normal for compressible fluid flow.
I know.
People use many times.
I think there can be some cases where you have to be careful when you do it. If you, I think from disks, if you do it and you were using angular momentum conservation to handle your radial momentum equation, it can cause problems. But otherwise,
In Faber averaging.
yeah, because there's a turbulent pressure which gets dropped when you're doing it in that form.
Our problem is now to parallelize this code, which is quite difficult for us. Because, you have student who knows LES, who did code, then he is going to America. Comes another student, he needs to study this code, he needs to study this method. And then again goes.
You mentioned the Godunov code
Yeah.
simulations. One of the results from the people in San Diego, Alexis Kritzuk, for example, is that, is that the spectrum of not of the velocity, but the velocity weighted with the density to the 1/3 power has a k to the -5/3 Kolmogorov-like spectrum. And that's rather unexpected.
Yeah, I know, but
Almost,
what is important, we can't see that they talk about this scale invariance or inertial aspect, but they don't show how they reach stationary solution. You understand?
Yeah.
It may be that this is a result non-stationarity still.
Oh.
Because this computation should be computed.
That would be
and-
surprising. I don't know that detail.
Yeah.
No.
Because there are, I don't know in reality, but when I was in Italy, but we were in this meeting, and I talked to people doing compressible modeling, Luca Bifirale, and he says that he tried to reproduce these computations, but he don't reach stationary solutions. So inertial interval.
It was forced turbulence, and
Yeah,
I
forced
actually
turbulence,
checked
yeah,
it
but-
myself.
Yeah.
I checked it myself. It was
Yeah,
certainly
so,
not bad.
and you reach stationary? This is only what I know. But I think that Godunov method is good for high Mach number, of course.
Any other questions? Matthias, please.
So one could say surely that subgrid scale modeling is to be subsumed under the general term of mean field theories. Certainly. The difference to what we usually refer to when saying mean field theory is, as far as I understood, that you don't have Reynolds averages. Right.
In
We
our
usually-
computations, yes. Then
we
you
usually
can
assume-
do Reynolds averaging after making runs. You may do, if you have, this random runs, you may do rate averaging.
No, I mean, if you do the theory before doing runs, then you don't assume that these averages obey the Reynolds rules. And we usually assume that.
Yeah.
That's the only.
But there is another now.
Is this correct?
Yeah, it's correct.
This
But
seems
there
to be
is-
the only
Yeah,
difference.
there is another story now. There is now Gibrid, Reynolds, and LES method.
Yeah, but my question is, we in some sense do something which is simpler, because we have the simpler averaging rules and you have. And we get some, from the structural point of view, some characteristic things like alpha effect, like
But you
archive.
get mean form. You
Sorry?
get mean form. But what we get turbulent form, from which you can get again mean form and statistics.
No, that's
In Reynolds
we-
averaging, you will never have statistics, because statistics is.
I don't see this difference. Because we deal with turbulence effect too. So
Yeah, of course.
What we refer to in mean field theories could be turbulence, and what you do is turbulence. So there is some parallelity. And we get, from very general consideration, but with the Reynolds rules, something like the alpha effect, something like the arc effect, or the lambda effect. and in addition something like turbulent diffusivities.
Yeah.
So my question is, if you do something which is more complicated, I would expect from the structural point of view that you get at least the same structural complexity we get. So that you need to incorporate into your subgrid scale something like alpha effect and so
Yeah, of course.
Is it the case?
Yes, of course.
Yeah.
If you want something like, okay, not to use two-scale approach or something like this, also here.
But indeed, you not only modify the turbulent diffusivities, you really plug in qualitatively new terms
Yeah.
in the equation,
Yeah.
which look like an alpha turbulence.
But there is no alpha turbulence here.
Why not? Because it's helical.
Huh?
Because it is not helical.
Because it's not helical, yeah.
Okay. But if it were helical, you needed to put in such a term.
Yeah, of course.
And
You
you
need
would-
another parameterization. Like, Gala-Levin did for atmosphere. You know this because her computations in convection.
Who?
Levin
Yeah,
compared.
Levin, yeah.
And she
Yes,
did,
sure.
because you read this article, as I know.
Mhm.
Yeah, of course, you may do non-trivial parameterization using helical parameterizations. Yeah, why not?
But what you do at the moment, basically, is to put in where in the original equation the molecular diffusivities are something more complex. Is it what you basically do now?
No, basically what I do now in this direction, I'm trying first parallelize this and to apply to the projects which I have.
No, I mean on the level.
But
of
in
theory.
science, yes,
In the theory.
because we have many interesting things like using, even introducing helicity in boundary layers in earth science, which should be much simpler than in images.
But again, if you prepare your equations, because you start with the original equations,
Yeah.
which have no everything, then you have to prepare them for to be plugged into the numerical code. So you have to modify these equations.
Yeah.
What is exactly the modification you do?
Modification is that I have some filtered quantities which are announced but not the same as Reynolds stresses, and make parameterization.
And what it does, say me for instance for the viscous term, what looks the modified term like?
But if it's Smagorinsky, it looks like the same. If it's
Yeah, but this is a certain model.
It's
So
a-
what does the series say from the general point of view? What it should look like?
I think in decaying turbulence it should look like, but if you have inverse cascade, it's no anybody knows. It's open problem. How to do
Okay.
backscatter? This is just people are discussing it.
I mean, for example, if you have isotropic turbulence, it's certainly justified to have an isotropic tensor, which the Smagorinsky viscosity
Yeah.
essentially corresponds to. If you have more complicated flows, maybe shear flows, could there be terms which are not included in the Smagorinsky expression?
No, you need anisotropic viscosity terms, of course. I
Yes.
don't think that
That's,
this type of, okay. No, this is for
so
homogeneous.
is that understood how to do it correctly?
Yeah.
I mean, people are always saying in astrophysics one has to use LES, but nobody knows how the correct LES actually looks like. You can do an incorrect LES all the time, but in these, that's exactly what he is asking. There are very strong reasons to assume, to expect a number of complications that we know.
Yeah, of course, if you have shear, it's a little bit different. For shear flow, you have different Reynolds stress, and of course you have different subgrid scale. But okay, it's next step, of course. Problem is first to be sure that when you have magnetic fields and compressibility, you have something. Because it's not obvious, you understand? That which is very simple for non-compressible, which works here. at least. And what is more difficult, for some reasons I don't understand clearly, this Smagorinsky model works well for compressible MHD, but people on atmospheric science sometimes don't like it, because they say that they have another models, even scale similarity, which is better and comparable. This is maybe because we have two types of spectra, and they have.
I mean, you had a Smagorinsky-like approach for the magnetic diffusivity.
yeah.
is there any serious derivation that this converges to the proper
No,
definite equation?
no.
And I mean, for Smagorinsky, I think that's maybe one of the only cases where there is actually derivation, which shows that you actually converge to Navier-Stokes in the limit of high
Of course, we
resolution.
don't derive. We consider this is correct for magnetic, at least, equation, for magnetic induction equation. But I think it should be derived, yeah.
Mhm.
But this is huge problem, how to put inverse cascade, backscattering and so on and so
In
on.
comment to Matthias's question, the difference between standard mean field theory and LES is that in LES one is talking about the case where the averaging scale is much smaller than the eddy scale. The eddies are much bigger typically. The eddies are resolved by the turbulence, and you're actually
Some.
averaging.
Some of them.
Yeah, some of them. At least the energy carrying scales, they are all being resolved. So we are in an extreme case where we are looking for mean fields whose scale is much, much smaller.
But from the theoretical point of view, this is not that relevant, like the point that we in one case are obeying the Reynolds rules, in the other case not. That is the major difference for me. Not that some of the eddies are resolved in that case, what we are usually not doing in the other case. This is not the basic difference.
No, this is
The
the
underlying
basic
theory is
difference.
just that different if you don't have the Reynolds rules. Because you get a lot of
Yeah.
different terms,
Yeah.
which we usually not consider. And that
Mhm.
seems to be the basic
No, there are special studies for how Reynolds approach, relates to this approach. For, of course, for atmosphere, but not for here.
I think there will be something to think more about maybe in the discussion, maybe after this talk, where we should think about a good case where one can disentangle and really identify non-Reynolds rules effects. I'm very unclear what that actually means. You showed triple correlations in the first part of your talk. Do you remember?
The second part. On first part, yeah.
What was that about? I mean, and then afterwards you immediately
It
said
was,
you neglect
it was
triple
about
correlations. And then there was-
heat conductive. For heat conductive, you have
Can you show us
Newton.
maybe these were triple?
Huh?
Can you show us again? Would be interesting to see what that was. Right, because that I thought was something new then.
Yeah, but it should be again written in outcome, which is more comprehensively written.
Yeah, here,
You see,
exactly. Yeah.
This is just to compute such type of things. Because these are subgrid scale terms which come to compressible equation due to appearance of magnetic fields. And we use normal central moments and so on and so on, because we...
Mhm.
And if you want this algebra, it's our Fischler's article, it's very...
So, Amy, do you have a closure for these
Huh?
expressions? Do you have a closure for
Yeah,
these
yeah,
expressions?
yeah. It's developed, but it's too much algebra, I don't put it here. The result is...
Okay.
Yeah, of course. And it's published already in Fischler's.
Okay.
But referee report was that he, in some sense, don't agree, but he recommends to publish because it's important. Because he don't knows how to do this correctly. Well, better, at least.
I see. Okay. If there are no further questions, then let's thank Araku again.